Hi, I'm Elizabeth with Logic Walk, and welcome to Chapter 6, the final chapter of the Computer Architecture 2 course. So far, we've learned how various I/O devices interact with a computer, and we've seen those interactions in action using the Logic Walk simulator. In the last chapter, we built a simple shell program that added storage and networking features. That shell followed a straightforward pattern. Sit idle until the computer is interrupted by the keyboard, hard drive, or network device. Then, when interrupted, run the corresponding subroutine, and then finally return to step 1. Now imagine this scenario. The computer is executing step 1 when a user presses the key. The keyboard interrupt causes the computer to jump to instruction 1 and begin the subroutine to print that key to the display. Before it can finish and signal the display, a network device fires an interrupt. At that moment, the computer saves its current PC value into memory cell 4, so it knows where to return, and then proceeds to process the incoming network message. Once a network message is handled, a jump R instruction uses the saved PC in cell 4 to jump back, and the computer resumes printing the original key, and then finally returns to what it was previously doing, which in this case was sitting idle. But what happens if a third interrupt arrives while the computer is still processing that network message? Let's build on our previous example to see the problem more clearly. The computer is running at p equals 0 when the user presses a key. It saves 0 into memory cell 4 and jumps into the keyboard interrupt routine. While still in that routine at PC equals 15, a network interrupt occurs. It overwrites memory cell 4 with 15 and jumps into the network interrupt routine. Then at PC equals 20, a third interrupt from the hard drive arrives. It overwrites memory cell 4 with 20 and jumps into the hard drive interrupt routine. When the hard drive routine finishes, the computer returns to PC equals 20 and finally resumes the network routine. Once the network routine is finished, the computer is unable to resume the keyboard interrupt routine because it lost the return address, which was PC equals 15, when it was overwritten. How can we prevent these older PC values from being lost? One way to handle multiple interrupts without losing our place is to push PC values onto a stack, which is just a small group of memory cells plus a pointer cell that marks the top of the stack. When the computer pushes onto a stack, it stores the current PC value at the address in the pointer cell, then increases the pointer by 1. When it's ready to resume the previous subroutine, it pops the value at the top of the stack, decreasing the pointer by 1, and then jumps to the popped value. Let's revisit our previous example by showing the stacking routine. The computer is running at PC equals 0 when the user presses a key. PC equals 0 gets stored at the top of the stack. The computer increases the pointer by 1, then begins handling the keyboard interrupt. While in that routine at PC equals 15, a network interrupt occurs. The computer pushes 15 to the top of the stack, increases the pointer by 1, and begins handling the network interrupt. Then at PC equals 20, a third interrupt from the hard drive arrives. The computer pushes 20 to the top of the stack, increases the pointer, and begins handling the hard drive interrupt. No more interrupts arrive. Now the computer begins popping the stack. After finishing the hard drive routine, the computer pops the value at the top of the stack, decreases the pointer by 1, restores PC equals 20, and returns to finish the network routine. When the network routine is done, the computer pops the value at the top again, decreases the pointer by 1, then restores PC equals 15 and finishes the keyboard routine. Finally, the computer pops one last time, decreases the pointer, and restores PC equals 0 and resumes exactly where it was before the first interrupt. This is much closer to how real systems behave. Computers routinely juggle many interrupts. Stacking return addresses ensures each task can pause, then resume correctly, so nothing gets lost. You might have noticed that in our simulator, we didn't implement the stack approach. That's because handling it can get tricky. Interrupts can strike at any time, and anticipating every possible failure scenario is no small task. That concludes the Computer Architecture 2 course. We explored how I/O devices, displays, keyboards, disks, and networks interact with the computer. Practice those interactions in the Logic Walk simulator and finished by seeing how stacks enable clean handling of nested interrupts and concurrency. Thanks for learning with me. When you're ready, keep building on this foundation. There's a lot more to discover here at Logic Walk. See you in the next course.